Hello, and welcome to another URSA example video. In this one, I'm going to start by explaining some updates to the website, and then I'm going to derive Gauss's law from the electromagnetic field Lagrange density. So updates to the website, just going from the top down, I've improved the load time a little bit, so it's about twice as fast as it used to be on my PC. It's still not that fast, but I'm trying to keep it reasonable. Another thing next is that these trees here, there used to be just rules and assumptions, and I mentioned in an earlier video that assumptions was too big and doing too much. So I've pulled it apart like pulled pork, and now it's tables and assumptions. So there's two things here. Then, as you go into these trees, there are now nice tables here, instead of just text definitions for all of these things. It's broken up a little bit better. And the tables have controls. So you can edit things, you can copy the definition to your clipboard, and there's a trash can for deleting things, and there's an add row button, so you can add rows through this. And so we've got these tables here. Now, also, under each of these trees, there used to be subtrees that said built-in and user, and those are gone now. They have been replaced by this column that is called source, and this tells you where a declaration came from. So when you load the page, the sources are all going to be URSA, because every declaration is from the built-in set. But then if you add anything, the source will be workspace. And that's about it. You can also pin tables so that they will show up above your equation without having these expanded, and I'm not sure if I'm going to keep this feature. But in any case, let's go. I'll explain more as needed. So let's derive Gauss's law. So here is our electromagnetic field Lagrangian, and we're going to use this to derive Gauss's law. Now in the Lagrangian formulation, the Lagrangian, or rather the Lagrange density, is a function of space and time, 3 space coordinates and 1 time coordinate, and the Lagrangian is defined in terms of some parameters, which are, in this case, the electromagnetic 4 potential. The electromagnetic 4 potential consists of two things, a scalar potential that's 1-dimensional and a vector potential that's 3-dimensional. So taking those together, that's the 4 potential. And so this is the Lagrange density, and you derive equations of motion by taking derivatives of the Lagrange density with respect to some elements of that 4 potential. And then where the electric and magnetic fields come in is that they're defined in terms of the 4 potential. So that is, again, phi and A, the scalar potential phi and the vector potential A. And E is defined as this, negative the divergence, or the gradient of phi, minus 1 over c times the time derivative of A, the vector potential, and then B is also defined. It's the curl of the vector potential. So we're going to start with this and derive Gauss's law. So the first thing that I'm going to do is enter these definitions, just these two things. I'm going to do that by setting my expression to each of them and then using a command to save it as a definition. So I'm going to set E equals negative del of phi minus 1 over c times the time derivative of A. And then I will use /save, turned on caps lock there, equality phi, or equality E, I mean. So this is now in the tables tree. There's a table called equality, and it says that there's an equality that's named E, and it says that E equals this stuff that we just typed in down here. So this is sort of defining E. And now I'm going to do the same thing for B. Set B equals cross del with A. So that's the curl of A. And then I'm going to say save equality B. So now that also shows up in this table. So we've got equality E and equality B, and these both come from the workspace. and their definitions are basically what I typed in. Equality B says that B equals cross del with A. So there are a couple more things that we're going to need to define. One is some constants. The Lagrange density formulation uses the speed of light c, and it also uses epsilon naught and mu naught. So those are all constants, and we're going to need to declare those. And the reason that we need to declare those as constants is that when we're taking derivatives, the derivative of any constant is 0, but Ursa doesn't know that c is a constant unless you tell it. So it will not just rewrite that as 0 unless c is declared to be a constant, or at least independent of the thing that you're deriving with respect to. So I'm going to add those as constants. And I'm also going to add the charge density and the current density as constants. They're not actually constants. They are functions of x and t, space and time. But it will be fine because we're not actually taking any space or time derivatives of them. But really, strictly speaking, I shouldn't define these as constants. I should define these as just being independent of the requisite things. And this, I accidentally put in phi here, so we'll just edit that and change it to rho, the charge density. Okay, so that's all the constants we need to define. We need to define two more things, and then we can put in the Lagrangian and go. So one of the remaining things is we need to define the Lagrange density parameters. So this is telling Ursa that phi is the scalar potential and A is the vector potential, and these are the parameters that we have in our Lagrange density. And the reason that we need to do this is that when we take derivatives with respect to these, in that Lagrange density formulation, phi and A and all derivatives thereof are independent from one another. So if you have a derivative with respect to one of another one, that's just 0 by the constant rule. And this sort of indicates to Ursa that those things are independent of one another and that those derivatives can go to 0. So that is now a table, since I just ran that. Lagrange density parameters is defined by the workspace, and it's scalar phi and vector A. And now, last thing that we need to define we need to tell Ursa what coordinate system we're working in. And this will be important for using the summation convention in this coordinate system, and it will also be important for enabling Ursa to take more derivatives just automatically and set them to 0. So I just defined that table, and it now shows up here. Sources, again, workspace. So now we can put in the Lagrange density and derive Gauss's law. So I'm just going to put in, I'm not going to use these x and t arguments. I'm just going to type it in without those. So we will set our expression to the Lagrange density, which is minus rho times phi plus the dot product of j with A plus epsilon naught over 2 times the magnitude of E squared minus 1 over 2 mu naught times the magnitude of B squared. So there's our Lagrangian, and the way that we use this to derive equations of motion is we need to take derivatives with respect to those Lagrange density parameters, which are phi and A again. So we really need to be working in Lagrange density parameter land. And we have E and B here, the electric and magnetic fields, so we need to rewrite those using their definitions, going back to the 4 potential. We need to be in 4 potential land for this. So I will use the bottom-up rule, bottom-up recursion scheme to substitute the definition called E, and this will rewrite E using its definition, and then substitute B using its definition. So now we've got this rewritten in 4 potential terms, and we can use the Euler-Lagrange equations and derive Gauss's law. So we're going to use that Euler-Lagrange equations for the phi variable. This will add some phi derivatives to both sides. And so this is now the equations of motion, or the equation of motion for the Euler-Lagrange equation taken with respect to phi. And this is Gauss's law. It's not simple yet. It's not been simplified, but we're going to do that presently. So I'm going to be using some motion commands. There are 4 motion commands that I'm going to use most often. One is in, and basically the curly braces indicate what part of the expression is selected. If I use the in command, it'll select inward, basically one step. Then if I can also use the right command to select rightward one step. If I use right, or its abbreviation R, it'll select the right-hand side of this equation. Left, or its abbreviation L, will select back leftward, and then out selects outward. So we can kind of navigate the expression that way. So I'm going to just take this derivative on the left-hand side by doing derive. And it derives this far. It's able to tell that a lot of those things are 0. And this remaining thing, besides the negative rho, this is also 0. And Ursa really should tell that on its own. It doesn't, and I'd like to fix that. But it is 0, and we can just go in here and use the constant rule manually, and that derivative is 0. And again, that's because it's a derivative with respect to phi, which is part of the 4 potential of the curl of A, which is a derivative of part of the 4 potential, and these things are independent from one another in the Lagrangian formulation. So typing in constant rule, this is allowed because we have this declaration that the parameters are these 2 things. So now we can go out, and this term is just 0, so we can just use simplify, and it'll just get rid of that. So now the left-hand side is good. That's just negative rho. On the right-hand side, we now have dd mu of this object. Mu is a repeated index, and it's eliminated using the summation convention. So we need to use that. We're going to use the summation convention to eliminate mu, and we're going to replace it with each element of the Lagrange density coordinates, which again I defined earlier on, and that's t, x, y, and z. So using this, we now have this sum. It's the sum of t, x, y, and z substituted in for mu. Now, I've done this derivation before, and I know how it goes, so I'll just keep carrying it out. This top term is just 0. So I'll go in here and just simplify that away. Take this derivative, and it's almost able to figure it out again, but again, we have that issue that I should fix where it doesn't figure this out automatically, and it should, but I'll go over in here and use the constant rule again. This is the derivative with respect to phi of the curl of A, or the time derivative of phi of the curl of A, so I can just use the constant rule and that goes to 0. Then I can simplify this. Simplify does not take the derivative of 0. It's actually configurable and you can make it take the derivative of 0, but it doesn't. And I won't show that in this video, but anyway, I've used the constant rule there and got rid of that. So now we've got these 3 remaining terms, and we need to rewrite these and simplify them. Now, Ursa actually, in addition to in, out, left, and right, it has multi-select. If you use in all, it will select each subterm of the term that you have selected. So now we've got each of these 3 things selected, and we can operate on them all at the same time. So digging in here a little bit, we can use the derive rule to take this inner derivative, and then it takes that derivative, but we can simplify a little bit more. This right-hand term is just 0, so I'll just use the constant rule here, which, again, Ursa should do automatically, but doesn't at this time, and then simplify that away. Then, this first little bit in here that I have selected right now is just the E field according to our definition. So I can use substitute E to change that back to E. And then I can simplify this a little bit. I'll go in here and take this inner derivative, which is a gradient. So that has gone from gradient to phi to d dx of phi x hat plus d dy of phi y hat and so on, which is the definition of the gradient. And now we're taking the derivative with respect to, in the top case, it's with respect to d dx of phi, which is this right here, d dx of phi. So when we take this, this derivative will be x hat, this derivative will be y hat, and so on. So we do that and just takes the derivative. And now we can almost just rewrite this. I need to get out of multi-select mode, and actually there's not really a good built-in way to do that. But I can use the special deselect selector. This is currently how you get out of multi-select mode, is by deselecting and then using the top selector to reselect the top of the equation. So actually, I need to be in multi-select again. I forgot to do one thing. I need to get this minus sign moved out of these derivatives, which I'll use bottom up commute neg. And the commute rule just tries to commute an operator with the other operators in the expression. So commute neg is going to try to pull this minus sign out, basically. So I run this and it pulls the minus sign out. And then I'll dive in here again, and here we've got E times X hat, and we've got E times Y hat, which are the components of E. And there's a rule called vector.component, which rewrites that dot product as the component of the vector. So now we've done that. Now I'll deselect again and select the top level equation. So now we've got this sum on the right-hand side, and the summation convention rewrites it using the split layout, which I explained in an earlier video, but now this is pretty small, and we can just switch to default layout. And now I will commute this minus sign out again. I'll pull out the minus sign using commute neg. So the minus sign is pulled out. And then I will use factor epsilon naught to factor out the epsilon naught. Now this thing inside here, this is the divergence of E. And there's a rule called divergence, which since we have this thing and it is the divergence of E, this will just rewrite that as the divergence of E. Now we've got negative rho equals negative epsilon naught times the divergence of E. And we can just sort of eliminate this minus sign. The easiest way to do it right now is to use the congruence rule, which I also used in earlier videos. The Kong rule applies a function to both sides of an equality. So if I use that here, we get double negations on both sides. And then if I use simplify, it'll just eliminate those double negations. Then I can divide both sides of the equality by epsilon naught and simplify. And we've got that the divergence of E is rho over epsilon naught, which is Gauss's law. So there we go. That's it. I am planning to do a video on Ampere's law in the future, but that's all for now.